Look at this visualization comparing energy densities. On one side, we have an overflowing pile of coal weighing 1,800 pounds and dozens of oil drums totaling 150 gallons. On the exact opposite side, balancing the scale perfectly, is a single cylinder of enriched uranium, roughly the size of a peanut. The path to understanding that kind of density took over a century. German chemist Martin Heinrich Klaproth first identified uranium in 1789, but it took until 1938 for physicists like Otto Hahn to prove that the heavy atoms inside it could actually be split apart. In this grid representing natural uranium, 99.3% is the inert isotope U-238. To get power, we look at the remaining fraction. That brightly glowing 0.7% is U-235, the reactive isotope sustaining a chain reaction. Extracting it isn't simple. You can't just sift it out with a physical screen. The entire nuclear enrichment industry exists to perform one highly hazardous task: pulling apart two near-identical isotopes to isolate that microscopic fraction. To harness this density, engineers must rip radioactive rock out of the earth, strip away the useless mass, and concentrate the volatile 0.7%, all while ensuring they don't trigger a weaponized chain reaction. The supply chain starts far underground. Deep in the Canadian province of Saskatchewan sits the highest-grade natural uranium deposit on Earth. But there is a massive obstacle sitting directly above the ore, a thick layer of sandstone completely saturated with groundwater. Digging straight into it would instantly flood the mine. To get through, engineers deploy an extreme solution. They drill 200 boreholes and pump calcium chloride brine, chilled to -22 degrees Fahrenheit, directly into the rock. The sub-zero liquid freezes the underground aquifer entirely. That frozen ice wall acts as an impermeable shield. It allows remote-controlled drills to safely break apart the high-grade yellow ore without flooding the cavern or exposing the miners to deadly cave-ins. Freezing the earth secures the raw material, but breaking the rock is the easy part. The true test of separating subatomic isotopes begins on the surface. At the processing mill, the raw ore is crushed into a fine, sandy slurry and bathed in acid. This dissolves the uranium, leaving the useless minerals to settle at the bottom. But the U-235 and U-238 isotopes are still chemically identical and bonded together. You cannot separate them as a solid. The material has to be converted into a highly corrosive gas called uranium hexafluoride. Once gaseous, it is fed into massive, repetitive rows of tall cylindrical machines, high-speed gas centrifuges. This top-down cross-section shows exactly how the subatomic sorting works. As the cylinder spins at immense speeds, the fractionally heavier U-238 particles are pushed outward toward the walls. The fractionally lighter U-235 particles gather tightly in the center, where they can be successfully siphoned off. For a commercial nuclear power plant to function, this gas only needs to be enriched until the U-235 concentration reaches roughly 3 to 5%. Pushing the centrifuge further enters dangerous territory. Enriching the gas above 90% U-235 creates weapons-grade material. It's a reality permanently scarred into the flattened landscape of Hiroshima. The centrifuge array is a precise physical filter. It operates on a razor-thin margin, separating particles by atomic mass to either light up a city or level it entirely. To safely transport and use the volatile concentrated gas, it must be chemically transformed back into a solid uranium dioxide powder. Using several tons of hydraulic pressure and extreme temperatures, that powder is baked or sintered into structurally stable, dense pellets. Those tiny pellets are then stacked inside long metallic tubes made of zirconium. This specific metal is chosen because it securely contains the radioactive material while allowing subatomic neutrons to pass through the walls freely. 37 of those sealed zirconium tubes are then bundled together with extreme precision, creating a highly structured fuel assembly. The microscopic 0.7% needle in the radioactive haystack has finally been isolated, concentrated, and securely caged for its ultimate purpose. Once delivered to the power plant, thousands of these fuel assemblies are loaded directly into the reactor core. In this simplified model of the chain reaction, you can see a stray neutron colliding with a densely packed U-235 atom. The impact fractures the atom, releasing a massive burst of heat and additional neutrons that go on to strike neighboring atoms. Zooming out from the atomic level, we can trace that heat. It boils the surrounding water into high-pressure steam, which spins massive turbines. A single reactor produces enough zero-carbon electricity to power 500,000 homes. But that process comes with a permanent cost. After about a year of continuous fission, the assemblies are spent. They emerge from the reactor intensely hot and lethally radioactive. To mitigate the hazard, the spent fuel must be submerged in pools of water 26 feet deep, where it will cool for decades. Today, over 700,000 of these spent fuel rods rest at the bottom of similar pools worldwide. That tiny uranium pellet represents a complex trade-off. We have learned to power our largest cities by manipulating the smallest particles in the universe, while accepting the permanent responsibility of managing